All right, last section of notes. This one is on how we induce an EMF in a moving conductor. So if you look here, I've got my wire right here, and I got a magnetic field pointing out of the page, but I've got a conductor that connects the wire that allows the current to finish, or at least to be completed. I'm moving it to the right at some velocity and at every delta t amount of time. Now, when I move it rightward, what I'm doing is I'm making the area of my loop bigger and bigger. So the universe doesn't like that change in flux, and what it's going to do is try and resist it. And by doing that, it's going to generate a flux. So if I'm moving my bar to the right, I want to know what is the direction of the EMF in the conductor. So just this part right here. Is it up or down? Take a second, think about it, pause the video if you need the time, but we'll talk about it in just a second. So in this case, my change in flux is greater than 0, which means I want to resist that. Currently, I have a magnetic field pointing that way. I want to resist it. So I'm going to create a current through my loop that goes clockwise. To resist that, I'm pointing into the board to cancel it out. My fingers are rotating this way clockwise. So as a result, my EMF, ooh, that's an ugly one, but it points from top down to bottom. So I've got high EMF at the top, low EMF at the bottom. How do we find what the magnitude of the EMF is? Well, it's just like before, we're solving Lenz's law, Faraday's law. And in this case right here, we have a loop with only one loop on it. So we don't need to worry about N. It's just going to be change in flux over change in time. Well, our change in flux, the magnetic field strength isn't changing, but the area is because it's getting bigger. So change in area over change in time multiplied by magnetic field strength. But our area, the length of this wire or this conductor is constant. So it's going to be length times however fast we're traveling multiplied by how long it takes. Well, our delta t's are going to cancel out. So we find that the EMF that we induce here is going to be equal to the magnetic field strength times the length of the conductor times how fast it's traveling. Now, you're like, okay, I understand why you can induce a current in one of those. But can you actually induce an EMF if there's no charges flowing? Well, technically, it's a conductor, and it's made out of charged particles. So when you move it to the right, even if there's nothing to connect it, I just have a bar moving, it can still induce an EMF. Now, charges aren't going to flow because there's nowhere for them to go. But you can end up with a higher EMF on the top or the bottom based on this. And to figure out which direction it's going to go, you just use your right-hand rule. So velocity is moving this way. Magnetic field is coming out of the board, meaning my force is going to be down. Meaning the direction that positive particles will feel in this is pushed downward. So we have a high EMF at the top, low EMF at the bottom. And the last thing we're going to talk about, it's not super important for it, for the AP test, but it's useful to know, are eddy currents. So we've been dealing with very thin objects where charges can really only flow one way. But let's say I have a big old metal cube and it goes through a magnetic field. How would the charges flow through that? They're just going to flow on the outside? What's going to happen? Well, eddy currents are the way these happen, or the way that flux is resisted. So they're formed in solid conductors when they're moved through magnetic fields, and you get lots of tiny, small loops. So you'll see, if you ever look at a diagram with eddy currents in it, there's lots of small circles all going the same direction to cancel out the flux in large objects. And with that, we have finished our electromagnetism unit.